we're live on YouTube. Okay.
Okay. Thanks, Bolton, for making this happen. So I wanted to talk about Enigmap, which kind of builds on the theme from last week of SGX plus Oblivious RAM. But when I started trying to talk about Enigmap, I realized that this group hasn't really had a proper Path ORAM background / tutorial intro thing. So I think a lot of our time is going to go in that. And then Enigmap basically is optimizations of that for specifically the SGX setting. So we'll talk a little bit about that at the end. Hopefully that is good for everybody. And obviously there's time for questions as well. So the motivation actually for Enigmap, the paper, was private contact discovery, specifically starting with Signal. By the way, some of the, this image is taken from the Usenix presentation for Enigmap. And so, yeah, it's basically to help you find your friends on Signal. And so Signal had its own initial private contact discovery solution. So first you create a list of hashes for users' local contacts. And then initially what they said is, let's just look up these hashes in a set stored on Signal servers, and then you have to trust Signal not to keep any logs, which they said they didn't in their blog, by the way. But turns out that, if somebody forced them, then, or there was a glitch in the server, then they could technically do this. And I mean, really, there's a problem with this because contact info is pretty low entropy, so Signal could just figure out a user's local contact list by looking at these logs. So then the solution 2 that they came up with, I mean, they did, I think, a toy implementation of Path ORAM, which I mentioned earlier. And I guess the toy wasn't very good. So what they realized is use SGX. Not they realized, rather what they chose to do. And then what they said is, well, SGX doesn't have enough storage, that's why you needed the ORAM. So store most of the data outside of the enclave. Again, Nirla discussed this last week a little bit, because the SGX enclaves have very little memory in them. Now the problem is the access pattern might leak who's looking at whom, even if the data itself is encrypted. So then in 2017, they put out a blog that says, instead, what you do is you actually encrypt your whole batch of requests, send it to the SGX server, and it actually looks over the entire database to find the intersection, and basically does batches of some size at a time, which, I mean, that means that every single request is linear in the size of the database, right? So it's pretty slow. So in 2022, they put out a blog that you just use Path ORAM and you build a better solution. And this, by the way, was concurrent to the Enigmap paper that we'll be discussing in a bit. But I guess at a high level, let's think about the data structure they were even thinking about implementing. Specifically, they wanted to deal with key value pairs, so KV. This, by the way, is a bit more general, and I think maybe this is not exactly what Signal envisioned, but what the researchers that worked on this and that inspired some of the 2022 Signal work were thinking of, because it's just more general, right? Finding a key, even if the value is basically null, is still a bulk of the algorithmic work. So each key in a general oblivious map, by the way, could occur once or multiple times, but we're just going to stick to unique keys for simplicity. So basically each user has their data stored once in Signal server. Then you have an initialization algorithm, which is basically Signal starts off with a database before they even started using any ORAM or SGX or anything. So they first need to put this in. Then you can find a key if it exists. You can insert new keys. And in our case, we're just going to assume that it automatically deletes the previous entry, just because it's going to be simpler to understand that way. If it exists, or just doesn't, that the insertions are unique. Then you delete a key value pair is also a possibility. And the requirement here, and I guess this is a little bit of restating from last week from Nilla, is obliviousness, meaning you assume that the data leaving the access is the enclave is encrypted, but the adversary can observe access patterns, and an algorithm is basically oblivious, or RAM access algorithm is oblivious if the access pattern is indistinguishable for different sets of locations, for the same set of operations or sequence of operations, essentially. You can also like do some simple stuff to like make an insert look like a delete and vice versa, or a find to look like any of the operations, but usually in the literature you don't bother with that. So you just assume the adversary like can tell what exact operation you're running, just not where. Okay, so I guess let's go to the path ORM background, as I said. So the API here is a bit general, more general, like basic memory operations, just read and write. And this was originally, by the way, created for like client-server model, and now our client would be the SGX enclave, which has much smaller memory than some outsourced server, in this case, the untrusted SGX host, and they can store some small amount of data locally in a stash. At a high level, the server storage is like a binary tree. Each node is in the binary tree is a bucket. Each bucket stores a fixed number of data blocks. This is, by the way, just an overview of path ORM. So during a read, path is mapped. Basically, each path can be mapped to the leaf that is that it leads to, right? And that's just that entire path is read into the stash, and the requested block is remapped to another leaf, and the old path is written back. By the way, this doesn't actually have to be a binary tree, but that's what everybody uses because it's just simpler to analyze. So I guess then talking about these paths, actually these paths are basically what the server-side positions are. And what you say is that a logical position is an index. And you number the leaf nodes on the server side from left to right. And basically now the server side of a position, the server side position of an index is always a leaf. And there's basically a map that like stores maps like indices to leaf indices. And the invariant here is that a block IDX always sits on the same path from the root of the tree to the leaf as the leaf position index. So just then think about what the client-side state is, and we'll go into more detail in a second on the data structure. But on the client side, basically you have to store this position map, which is basically n positions and then log n bits for each position. How is this better than storing the whole array locally? Basically, the data blocks at a given index might be much larger than log n. And you can recursively create another ORM to store the position map, adds another logarithmic overhead, and then you have some stash to store any overflow of stuff you can't write back. We'll talk a little bit more about this at the end. So again, details on these server-side positions. So suppose that block 3 is mapped to leaf 0. So it can sit anywhere in this path. So basically, block 3 can sit in any of these red buckets. Hopefully everybody can see the colors. But it cannot be in any of the non-colored buckets when its position is mapped to 0. Now, suppose it's mapped to 0. It cannot be in this blue bucket. And actually, when you read it, you read the whole path since you didn't store where on the path the block is. That's how you like kind of reduce some of the storage overhead of this. And you initialize with some empty local storage of size z times log base 2n, where z is the size of the bucket. And log 2n is basically the length of the path, right? And you first pick out which leaf you want to look for, which leaf's path you want to load. by looking at your position map. And then for the entire depth, where this like capital L is the depth of the tree, you basically just add each bucket at every depth. So you just like traverse the path, load it into your local storage in the like trusted client storage, in our case SGX, and you read the specific block. Basically, you read all of this and find where the correct block with the correct index is. And then you pick a new position for this block. Basically, the other blocks haven't really been touched. It's just the block that you read that has really been touched. And reading it again, you want to kind of hide that. So you basically randomly pick a new position for it. And like these blocks are all like completely independently like chosen their like position. So that's why you don't need to pick a new position for everything else. Now, suppose our new position was this leaf 2. Now block 3 cannot be stored anywhere else except for the path to leaf 2. So when you write it back, the intersection is only the root node. So that's the only place where the block can go. Now, yeah, I guess that, so then I guess writing back, basically you, look at every block along the path, and you do a linear scan of all of the data blocks that you've loaded into your local data, and you see if you can put it in that block. So for example, if there's an intersection at like the middle layer of the tree, then you can put it there, but you can't put it any lower than that. And you basically just try to put things as close to the leaves as possible, and write them down. And this example has a really large number of buckets compared to the actual number of blocks. In fact, like, this is like a tiny example where like you basically have O of n buckets. So you actually can lower the server cost by having the bucket sizes being much smaller. So if your bucket size is 2, you can do something like this. This is the initial state. So you read block 2. After reading, you randomly remap it. Now that you've remapped block 2, you still need to rewrite the path to leaf 0. So you basically go through the array. Nothing can go here. So this is all dummies. You realize that actually block 0 can go in here. So you put it in there. And you pad it with a dummy. And then block 1, 2, and 3 can all only go to leaf 2. So you have 2 blocks available, but 3 things to write, and this is where you like end up with overflow. So how do you deal with this overflow? You have some stash that like keeps all the overflowed values. So then the next question is, how large does this stash need to be? So for a given sequence of logical access patterns, let X be the sequence of paths to read, Y be the sequence of remappings. Then basically let S be the like sequence of access patterns for the sequence of paths and remappings. They actually have a theorem in the paper that says that turns out like if you have a stash size R, capital R, you can basically get very small probability of failure by like having reasonably small stash, turns out. So the failure mode is basically that you like overflow your stash and you can't write back enough things, and then you basically like end up overwriting or corrupting data, right? So that's just for like their chosen bucket size. So yeah, I guess they basically prove how this is like oblivious, which you can kind of see, right? Every path is chosen completely uniformly, so you don't actually know which part of the path you actually needed to read, and so on. And then this shows you that you actually get correctness and you don't end up accidentally overwriting data with high probability. Okay. Now, I guess Enigmap, that was what was promised. So maybe before we talk about this, let's just see if there's any questions about Pathoram. I don't know if there's questions on the YouTube.
Any questions on YouTube? I don't see any questions on YouTube currently.
Andrew is asking a question. Can you maybe?
Yeah, sure. Question. Is there anything tough or unique about PathoRAM? I felt the description of what it does was clear, but not the design challenge.
Interesting. Yeah. Well, it's interestingly, the paper is titled PathoRAM, an extremely simple oblivious RAM protocol. And I think it was just the case that before this, it wasn't known how to do this. People did have trees, but they the eviction protocol, for example, was much more complex. Yeah, I guess once you see this, it's hard to see why it would have been difficult to come up with it. And since there's been a lot of work on top of this, but yeah, before that, just nobody had such a simple eviction protocol that worked. And didn't have high probabilities of failure. I mean, if you try to think of it naively, right? You want to hide access patterns from a server. Yeah. And also recapping the privacy claim. So, okay, so you want to hide access patterns from the server. So all the data is encrypted and stored on a server. All of this data at a high level is basically in an array. What you want is an API that, as a client, you can enter a pointer, run some local algorithm, call some physical accesses from the server, retrieve some amount of data, and then be able to run some other algorithm on top of whatever you retrieved to then get the value for whatever location you looked up, right? So it's literally just looking up values in an array. Now, what you want to avoid is if you were to look up values in an array on the server and just keep the data encrypted, the server, for example, could know if you're reaccessing the same value multiple times, or if the server knows what algorithm you're running, it could know, for example, if you're running a binary search, then it could know from the access pattern what ranges of values you might be searching for. So for that reason, you want to basically hide this access pattern, and that's what the guarantee is, that assuming the data is encrypted, the server doesn't even learn any statistics about which encrypted blocks you're accessing, and if you're accessing them repeatedly.
No, I mean the level privacy claim. Why is this particular protocol secure?
Oh, okay. Well, I mean, okay. Well, given that you're basically choosing, okay, so if we assumed that we have an infinite stash, and anytime there's an overflow, you can locally store it. In that case, you could basically do you were completely randomly choosing positions for particular nodes, and therefore the path is completely remapped every single time. So, and all paths have at least some intersection, so you basically can't look and be able to tell if you're repeatedly accessing the same value, for example. And then basically what they're saying is you don't even end up needing an infinite stash. Turns out that a smaller stash can basically allow you to do the same thing. That's I guess at a high level how they do this. Yeah.
Thumbs up.
Okay. Should we talk about Enigmap then? Unless there's questions on YouTube or...
Yeah, no questions on YouTube.
Okay. Okay, then I guess just let's go back to oblivious maps just as a reminder, dealing with key value stores, assuming unique keys. You have an initialization, find, insert, algorithms, and delete. So the thing is, this is a bit more complex API than what Pathoram was providing. It's basically what you need is like some sort of search for finding a particular key and its value. And searching for a key, you could do it in a simple array, right? But that's just, you need to then look up all of the keys and basically figure out which one is yours. You also can't even terminate the algorithm early if you want privacy, because terminating the algorithm early is like a kind of revelation of like access pattern, essentially. So what you could essentially do is you could use a tree to lexicographically organize these trees and then do a binary search. And then even if you fully do like a full binary search, even if you could have terminated early, you still only end up with logarithmic in the number of keys complexity for this. So Enigmap specifically says use an AVL tree because it's balanced and the depth won't leak things either. The like depth at which an item is placed won't leak things. And at the same time, you don't actually need a tree that's the same size as like the number of possible bits in the key either. So you store these tree nodes in an ORM, but then the question is how, right? Because I guess I started with an oblivious map talk. So I guess you just quickly store the nodes in an ORM. So here's how you could do it. You could, in each of the ORM blocks, you could have a position, a key, and then its left child's key and its right child's key, which would like then tell you what the next key is that you want to look at. And in the signal case, remember, like we don't actually have a value for the key, so just the key itself. And each of these ORM blocks would be an AVL tree node. But there's one challenge, right? So let's call this thing a pointer. Each ORM block, if that's a tree node, the SGX size is pretty small. So what you end up with is basically pretty high page swapping for each operation. Like each time you do a tree node lookup, right, you're gonna have like pretty high overhead. So now if you do recursive ORM to store the position map, then you basically have to do like page swapping both for the recursive position map and like the main ORM that stores the tree. So they actually try to solve this, actually, by the way, they're not the first ones to think of this. There are other papers, such as a paper called Snoopy and OblivDB, I think, Oblix, that like also take inspiration from this Oblivious Data Structures paper, which basically says you already have tree data structure in the AVL tree to store keys and ORM pointers. So why don't you, instead of having the block data just be like position key, left child key, right child key, be pointer, left child pointer, by which you mean the position, and the right child pointer, by which you also mean the position and the key. So this way you don't actually have to look up the position map, and you only need to keep the position of the root, and then you can just recursively look up the next position as you traverse the AVL tree. So that basically like gives you a logarithmic improvement and fewer page swaps for each block, essentially, that you want to look up. Okay, so that was the first optimization. Any questions about this? Okay, then there's a second optimization, which is, okay, so these blocks themselves, they're like kind of small. which means that if you load one block into the stash at a time, into the SGX at a time, you're basically kind of wasting the extra space that you could have used to do stuff. So like it just doesn't make sense to like traverse the outer path ORM tree one bucket at a time, right? So we know that if a bucket is paged in, I've written block here, but what I mean is bucket. You know that if an ORM tree node is paged in, some of its children will also be paged in. So what they say is, why don't we store the outer ORM tree using a locality-friendly layout? Meaning you page in multiple things at once, where you know that like the multiple things that you've paged will like allow you to make the next access within that page instead of higher page complexity. By the way, this like locality friendliness, this concept comes from caching literature, where the idea there is like you had like fast memory and slow memory back in the day when you had like tapes and stuff, and loading things from the slow memory was pretty inefficient.
We have a question. Any concrete performance for figures at this point? How much optimization are we talking about from the simplest page-aware optimization? Also, what kind of dataset sizes and value sizes are relevant?
That's an interesting question. So with regards to this particular like paper, they don't have performance numbers as far as I recall. For like individual optimizations, they only have performance numbers for the final thing. So like the previous one was page aware. I guess what you mean is like just for this tree stuff. I guess what you could say is because this has also been used in the Oblix paper, we'll see later what the asymptotic benefit of this is. Hopefully that's a satisfying enough answer for now. Yeah, but they don't really have full numbers for just this. Okay. Okay, so I guess the second optimization, this technique is basically similar to B trees. They use like locality-friendly B trees papers from the 80s, 90s. And essentially what they say is, there's a paper, for example, this Oblix paper. They are basically doing only the previous optimization, and then the way that they store things is in this like heap type layout, which means that like you don't always access leaves or nodes in the ORM tree that would have been accessed together and page them in at the same time. And they instead basically try to do that by like dividing things into like little mini trees that you know that parts of those mini trees would be loaded at the same time. Okay. So that's like their second main optimization. They do have other optimizations. So their initialization algorithm, for example, is more efficient because you're filling in page-sized ORM, page-sized buckets of the ORM tree at a time. They use like multi-level caching to get like better concrete performance. They compare with Signal's naive implementation, and here's what they say. Their findings show, Signal was basically saying PathORM wasn't good enough for them, and they're responding by saying our findings show the opposite at a database of size 256 million entries. By the way, this is an answer to the like, what sizes does this get relevant at? Enigmap outperforms Signal's linear scan implementation by 5.5x to 5,500x depending on the batch size, which I guess that's quite a range, but here the batch size is like how many queries at a time are you searching for. Then they provide also a concrete comparison with the non-cache optimized Signal ORM protocol. So this is like, I guess this maybe is an answer to your question about like, what if they only use the AVL tree with the like Oblix type layout? Then they get basically a 3x speed up. This paper gets a 3x speed up over over that particular thing for this database size. This was, by the way, like concurrent-ish work. The signal ORM was concurrent-ish with this Enigmap paper. And here's the asymptotic comparison that I promised. So if you have n entries in the map, so n contacts in the server, and you have a page size of 4 kilobytes, for example, that's the capital B here, and the enclave has resident memory M. So I think was this the what was it that you said last week, Nirla?
What?
ESG or whatever the
EBC.
EBC, yeah. I guess that's what this M would be, right?
That is, I guess the enclave page cache holds multiple pages. Multiple 4 kilobyte pages.
I see.
That they add up to
I see. 128, or to the entire EBC.
Yeah.
Okay, and yeah, I guess beta is the number of users you're looking for membership off at a time. Then you have this complexity. Basically, the signal that they're writing here, this is the naive signal protocol, so linear scan, using not locality optimized ORM. That's what this Oblix paper is. Gives you some speed up, and then finally Enigmap gives you a bunch more speed up basically on top of that. Mainly these logarithmic factors that they get from using the entire cache instead of basically using page sized blocks of elements at a time instead of a single thing loaded into a page at a time. And I think that's all I had for now. If there are questions, we can talk about that. Otherwise, we can also just take a look at the paper and I can just point out a few.
Question: isn't it counterintuitive that caching can help in ORAM?
That is correct.
That's actually an interesting question. I would like to understand more about can I just it's if I make a bunch of calls to my ORAM, can I just cache those and maybe it how exactly, because more than just hiding what you call, you also sort of have to hide when you call. So is it just the case that every fixed amount of cycles you make another call to the ORAM, and if you have a read that you want to do, you have to wait until it gets to the point where it gets to that particular CPU cycle where the ORAM access is finally allowed? How exactly is it the case that you or how do you hide when you're accessing the cache if you are in fact doing that?
Okay, here I guess maybe there's a couple of things, right? One of the things that this paper specifically in their cache awareness they discuss is you have a tree, right? You always have to access the higher levels of the tree, closer to the root. So if you cache those in basically some sort of more efficient memory or more efficient ORM, so I guess the outer untrusted server knows what each time you get a request from a user. So if you have caching just of the higher levels of the tree closer to the root in faster memory or smaller ORMs, you're just speeding up the number of tree levels that you have to access using a large and efficient ORM.
Sure.
So in that sense, it doesn't matter. The thing that so in that sense, you'll never get a cache miss if that's how you cache. Now, the question might arise, what if, for example, you had a bunch of stuff in stash and you found is a query came in, you found it right there in the stash, you've basically leaked that like 2 users have queried the same phone number, for example, right?
Right.
I think that would be the case where you have to hide
You
the
have to
cache.
hide by like accessing again, even though you don't like need to access, you have
Right,
to access
right.
just to like hide the fact that
Right.
you don't have to access.
Yeah, and also, I mean, this is an AVL tree, so you might end up with like getting like a search result right at the like top of the tree. That you will have to do the entire tree search, and that's where the AVL being like known depth comes in. So there, yes, you have to basically search the whole tree. But yeah, I guess 2 kinds of caching. One of them you will have to hide the cache miss or cache hit. One of them where you're just caching the higher levels of the tree, there it doesn't matter because that pattern is oblivious anyway.
Cool.
Yep. I guess other questions. Otherwise, actually, if we still have a little bit of time, do we, Bolton?
It's 12:40 now. I think we have time. I just want to make sure that I have time to like walk over to Siebel. So like maybe like 12:50 I'll want to get out of here.
Okay. Well, I guess a couple of things I wanted to mention. So, for example, they discussed this paper Obelix that they compared with. One thing they didn't do, which I found interesting, was compare with this paper, this other paper Snoopy, which is mentioned, by the way, in the... Oh, so you can't...
Yeah, we are still looking at your slides.
Sorry, let me just... Here. Okay, yeah. Here, this is the paper they do compare with, right? They don't compare with this other paper, Snoopy. I guess and by the way, these 2 papers are on my reading list, so, you know, if you thought this was interesting and you want, like, other stuff to look at, background, I do recommend these 2. I want to look at this paper because I don't understand why they didn't compare with this. I think it might be the case that they don't, like, provide like asymptotic improvements, but they do have like pretty solid like performance numbers in this paper, and this is a paper from 2021, so I wonder if it was just a case of like this paper came out in 2021 like towards the end of the year when they were like already like gearing up to put the other paper, the Enigmap paper, on ePrint, and so they didn't put the comparisons in. But I just thought it was a bit like disingenuous not to discuss it. So I wanna I guess go in a little more detail on this paper and see why it wasn't deemed comparable. So that's one thing. Then I guess what else did I want to talk about? Yeah, I guess the like big main thing that they like did that was like not in this particular like already ORM solution was the locality friendliness. So yeah, I guess I'm wondering like what, like they had a bunch of other improvements as well, but most of them were relegated to the appendix. I'm wondering how they like decided which thing was like the biggest factor. I guess maybe they just kept things that like led to asymptotic improvement, but I think this ties back to Andrew's question, like are there, I guess maybe I'll just bring that paper here as well. Is there like a reason that they don't include like the impact of these individual improvements? They do like have some breakdown numbers, right? But I don't think they have like super strong numbers on like individual improvements of added by like, for example, some of their like caching related optimizations. They just say we have an optimized version. Yeah. So they do have, I mean, that said, they do have a lot of numbers, and they did, like, obviously do a lot of analysis, but I'm just curious, like, if they could break down benefits of each thing, given that, like, their appendix has so many other optimizations. Oh, one other thing actually I wanted to mention here. They say achieving integrity and freshness. What this means is, how do you know that you're searching the right database, right? And they say they use a simple Merkle tree that is overlapped on top of the ORM tree to achieve this. Now, I have a little bit of a problem with this claim. Like, its additional overhead is 1 to 2%, because actually recently I found this paper. Memory checking requires logarithmic work. Overhead, right? And this paper basically gives you upper bounds on, like, lower bounds on, like, how efficient memory checking can be, meaning ensuring integrity of a data structure. And what they say is, like, basically, if you have local space P and query complexity Q, meaning that's how many extra things you need to load in order to get integrity, then this is, like, basically the relationship, meaning assuming much smaller memory space, you need at least this many, like, additional loads in order to ensure integrity, which means that if you do this on top of ORM, which is also, by the way, discussed in this paper later somewhere, let me see, they say that like, you actually will get another additional log n factor on top of, like, yeah, I don't know why the search is not very good.
It's a picture, not a PDF.
Yeah. Well, anyway, I guess TLDR, what they say is that the overhead on top of ORM of achieving integrity as an implication of their lower bounds is log n. So I kind of don't believe the 1 to 2% number unless, like, their integrity checking is, like, just that fast. There is, like, an asymptotic overhead to this. So that's just something I would like to point out and call out as, like, I wish they had a little bit more analysis of this. Or yeah, so, and by the way, this is in Appendix C5 here. I went through this overlapping Merkle tree structure with ORM tree. Again, like, there will be that log n factor, so I'm not sure exactly what they do. So again, you know, more papers added to the reading list, these citations here, to see how exactly they do it, because they don't actually discuss in detail. Okay. Any other comments or questions?
Well, I think I'm gonna turn the stream off and probably leave around now.
Okay. Thank you.